What we want to do here is that we want to define the types of energies. And the only way we can define the types of energies is with the work energy theorem. So the types of mechanical energies that we will deal with in this course is that anytime I have an external work done on a system, it's going to change its energy. That means it goes from state one, from 1 to 2. That difference leads to 3 types of energies that we will consider. One is the change in kinetic energy, the change in potential energy, and the change in thermal energy. So just going in that order, the first one that I'm going to look at is that I'm going to look at kinetic energy. And if I write the word kinetic energy, what I'm going to do here is that I'm going to abbreviate that with KE, but symbolically, the way we deal with it in mathematical equations is we write K. So as a reminder, work is the physical concept, while energy is a more abstract term. And one of the goals here is to show you why I make that statement. So let's try to do that. We will calculate the work done to, I think I want to put that in capitals. The work done to change the motion of an object. Now, what you're going to find is that because this happens so much, because this type of thing occurs often, we will define a shortcut not one word, for work done, which we call kinetic energy. So as an example, what we're going to do here is that suppose we get a sucker to push a car. So what do I see here? I envision that I have a car. And so when I'm thinking about my car, we imagine now that we have the smart one inside the car. And our focus here is only on the car. So what we're saying here is that our system is the car and everything in the car. And so what we imagine here is that suppose that this car is already moving at some speed. And now we have our sucker. So our sucker here is now pushing the car. And as a consequence, the sucker applies an external force on the car. And as a consequence, after some distance, let's say that I copy this car and I move it some distance later, let's say to about right here. And let me take some of this stuff out to just clarify it a little bit. This guy is still applying this. And what we're going to see here is that now there's a higher speed. And so when I start to look at this, we can see that the car has now moved some distance. Clearly work is being done. And because the displacement and the force are in the same direction, we could then claim that there is positive work being done. So from our free body diagram, we immediately conclude here is that there is only one possible work. We do have a normal force. We do have the weight of gravity acting on this thing, but we are seeing that the displacement is perpendicular to these two, so therefore there's no work there. So then this external force is the only one that's doing any work because it's in the direction of the displacement. So what we want to do here is that we want to calculate this external work. To calculate the work done on the car, once again, to change its motion. That's what we're interested in. We want to calculate the work done on a car to change its motion. We use two ideas. The first idea that we want to use is that we want to look at Newton's second law, and Newton's second law says that the external force is equal to mass times the acceleration. The second idea that we're going to use is we're going to use kinematics. So when I use kinematics here, what you're going to find here is that I don't want to, oh, look at that, I keep spelling it wrong. I don't want to go and draw in a motion diagram or set up a table. And what we're going to find here is that we're going to use one equation that reads like this. And the whole goal here is that we're going to focus on this delta x right there. So if I use these two things here, what is the work done here? So now I could come in here and say that the work done is then going to be the external work, which is going to be the force, the external force, times the displacement. And so here we go. We replace the external force with the mass times the acceleration. And next, what we want to do here is that we want to replace this delta x with that kinematic equation right there. And if I do that, I then have that I'm going to get v squared, v2 squared minus v1, and then I'm going to get 2a in the denominator. And what you're seeing here is that the accelerations cancel out. So as a consequence, we see that we can now rearrange this to read like that. So this is the expression for the external work here. So once again here, look at this term. This term right here, this is another way to write work done. And because we are changing the motion of this thing, and it shows up quite often, we then want to write this term in a different language here. So I'm going to say that once again, because this shows up often in mechanics and many other branches of physics, we define the following. What we defined here is that we take 1/2 mv and we define it as 1/2 mv squared. And this is what we call kinetic energy now. But this is not a meaningful thing, right? This is not meaningful. This is meaningless. What is meaningful is the work. So then we say that the external work is now going to be the change in kinetic energy, which of course is 1/2 mv2 squared minus 1/2 mv1 squared. So this here is how we define the symbol K, but this is the meaningful quantity. So this is meaningful. So again, if we start talking about what we mean by energy, if you're talking about a change in energy, then we could say that that is a meaningful statement. If you do not talk about a change in energy, then it's a meaningless statement, which you gotta agree that that is quite different than the language that we use in everyday situation. Now, if I look at the units, we can now see that the unit of work is now also the unit, even though I'm writing K, I should be writing delta K. This is our unit in the metric system, which is a joule. And so they are one and the same.